And sorry for cutting you off there.
Oh, sorry. Oh, no, you're protecting the integrity of our organization.
Oh, you know,
and people like me.
When I start seeing things, alarms going off. Oh, okay.
It took me a while to figure out what to do about it. Oh, I saw it in the email. I didn't read it carefully. I saw this automated generated stuff. I thought, oh, I don't know what to do. Let's worry about it time. Of course, the Blackbird can connect back and back. So this goes to
Hi. Not really. Yeah. It's not bad. It's fine. Yeah. 2000. Rent.
It is. I had my own. Would you mind that being part of it? Yeah, there's lots of good things. No, I thought about it on that book. And I had let's very cover it. So it doesn't have these stamps on it. The old ones have these stamps on it. No, you can't. No, you can't. There's no seat.
Good evening, everyone. Shall we get started? So welcome to the October meeting of the Royal Astronomical Society of the Victoria Centre. I see lots of unfamiliar faces. How many visitors do we have? Any new members? Welcome to all. You maybe convert some of you visitors to new members at some point. Just remember, if you need to know anything about us, any questions or anything, you can either ask right after the lecture, or we generally meet upstairs in the astronomy lounge after the meeting. And you're welcome to come up, whether you're a member or not. You're welcome to come up and join us for coffee and cookies and meet us and ask any questions that you might have. So like I told you, if I completely forgotten to download my agenda onto the screen, and this computer my screen, so I have to go off my notes here. My report, as usual, is in the Sky News, but there are a couple things to just remind you guys about. Remember, next month there's no general meeting here at UVic. Next month is our annual general meeting, and for those members who don't know yet, that's at the Astronomical Golf Course on Sunday, November 27th at 6:30. And we'll be sending out a package by email about that on the 15th, I believe, and it'll be on the website as well. So you'll be able to reply with your choice of meal, and how many people are coming, and you can reply directly to Nelson about that. And also in December, there also will not be another monthly meeting here at UVic. That's going to be our thank you party pizza night. So if you're an RASC Victorian member and you volunteered at any event, whether it's at the observatory or Astronomy Day or Beavers or whatever, in the last couple of years, you're invited to come along. We're going to have pizza, soft drinks, and coffee and stuff. And that will be Saturday, December the 3rd in the Gary Oak Room at Fairfield Community Center. So that's going to take the place of our regular December meeting. So no December meeting here either. So December 3rd will be the pizza party, members night, thank you party, and we'll have a short business session to make it legal as our December meeting. So no meeting here in November and none in December. The next time we meet here at the event will be on second Wednesday of January 2017. And I see Bruce is away tonight, but he did email me some details. So for his treasurer's report, he reports that there's $10,582 in the members account, $20 in our gaming account. As soon as he's over his cold, he's going to get to do their taxes for the year. And if anybody needs a check for reimbursement for any center business, there'll be an Astronomy Cafe this coming Monday. So pop down there and see him or send him an email. Secretary's report, Les.
Yes. I'd just like to note that the minutes of the 2015 annual general meeting will be posted soon on the RASC Victoria Centre website. And for those that are interested in such things, if you have corrections or additions to the minutes, it would be appreciated if you could email them to me, the secretary, ahead of the annual general meeting, and then we can minimize the interaction that we need at the meeting in order to get the minutes approved. Thank you.
I don't see Michelle around. He's probably gone upstairs to make coffee and cookies for us.
Oh, Michelle is at sea on the Cocoa Library tonight.
Oh, you've got library?
Yeah.
Okay. Membership, Chris.
The library. If you go on our website, scroll down a little bit, you will find a for sale item. And the for sale item is an antiquarian sky atlas by Barnard himself. If you have a spare 10 grand to rolling around somewhere and just want to buy it from us, we are located at Pine River Library. And if you know anyone who has 10 grand laying around as well, and want to do this, we'd be happy to hear from someone. So please pass on.
It's actually what I'm told, a fairly good price for a very rare and unique volume. So sounds a bit pricey, but it's actually
Asking price.
They have been known to go for quite a bit more, and it's not in quite as good condition either. Membership, Chris.
So our current membership is 235, And there are 11 people whose membership has expired in the past 2 months. So plus or minus 11.
Yeah, that's still a pretty good number. That's, we're still kind of right around that record.
We gotta keep it around 220 net, I guess.
Yeah. That's good. Sky News, Reg.
Good evening, everyone. Issue 381 is historic in nature. I think it's the first time we've ever had a letter to the editor. The other thing is we have an article in there about a close encounter with a supernova. When I first started studying about it, it was released this summer of the announcement, and it was by a group of German scientists. And the person who actually led the project and designed it was a Canadian. His name was Sean Bishop, and he did graduate work at UVic. So check it out. And I have copies if anyone. I looted a number of hard copies if you're interested in seeing it at the end of the show.
Yeah, and it's available online on our website too for non-members who want to look at that. And Reg has been doing this an amazing job with that. So thank you again, Reg. School outreach. Anything to report, Sis or Liz or Lori?
But the schools are the public outreach.
Schools.
Schools, yes. We are going to be for the next 2-3 weeks. The floodgate has opened. It took a long time for it to do that, but we are going to be busy tomorrow, on Friday, Monday, next week, sometime, and then 2 weeks will be completely full for us. There is a potential night sky viewing coming in November. One of the schools have requested that we do go to their school for night sky viewing, and it's the weather dependent. If you would like to offer your service, please let me know. Otherwise, I will be in touch with you. So whatever is good for you, so that's good for me too. Anyway, it's going to be very busy 3 weeks for us. Thanks to Lori for all the hard work she's doing. Thank you.
Do you have a date for that November observing?
No date yet set.
Okay.
Have to look at what the moon will be doing.
Good. Thanks. So just a recap of the summer Saturdays at the observatory, including the September 24th final one. There was 2,415 visitors came in. Over the course of 14 Saturday nights. And considering that almost half of them were kind of clouded out, including the first one and the last one, and a whole bunch that were in the middle. I mean, the fact that people came up at all is absolutely amazing. And they wouldn't come up if it wasn't for our volunteers who just did such an amazing job. So I can't say thank you enough to all the volunteers from RASC and friends of the DAO for coming out, rain or shine, and just absolutely wowing over 2,000 people. Just with your skills and your knowledge and enthusiasm, it's absolutely amazing. So thank you again, and that's kind of partly what the December meeting is for. It's just that let your hair down pizza party and say thank you to you guys, because it wouldn't happen without you. So thanks again for that. On the website, Joe.
Third part for any time.
Seems to be, yeah, thanks. Matt, tech stuff.
Just pull up the stats from last month. Give me a half second here, sorry. On the main site, we had 2254 visits with 1,682 users. That's pretty much the norm. Looks like we had a spike on Friday, September 16th with 236 visitors all at once. Not sure what that's about. Nothing more for the website, and for tech, making a backup of the machine up the hill. Been saying that for a little while. Ran into some issues with it. Once that's done, we'll be swapping over to the new machine. I know Michelle is on my case to get things ready for his Pleiades project, so I'm gonna have to get myself up there pretty soon. So.
And we do have visitor access to the visitor Wi-Fi up there now. I checked out on Saturday, and it's really weak. It's like barely one bar on my iPad. And it took 2 or 3 tries for my iPad to find the signal.
And this is from the observing deck?
It's from the center of the universe building beam down to that VCO.
Right, but you were,
I was on the deck,
Yeah.
yeah. Because it was cloudy on Saturday. On Saturday, I didn't want to open the roof, but there's no way you can pick it up inside.
No.
When the roof is rolled back maybe, but it's technically there, but it's,
well, if you recall, I kind of mentioned that would probably be an issue for that frequency. Let's see.
yeah. So Dennis said to check it out. I did. So technically it's Wi-Fi, but it's.
I'll do a site survey and see what I can suggest.
Okay, Lori, do you want to talk about that FDAO thing?
Yeah. So it's not finished. This next Saturday, not this coming Saturday, because we're gonna be raining cats and dogs. But next Saturday, October the 22nd, we're going to be opening the Center of the Universe and the DAO for one more Saturday night. We keep kind of saying encore, and we just keep going here. We're going to be having Hawaiian night. You are all to wear your Hawaiian shirts and we have our presenter is Mary Beth Blake she's the outreach coordinator for the Canada France Hawaii Telescope, and she's a marvelous speaker, and she's going to be here actually all week. Starting on Sunday, and staying over until another Sunday. She's doing programs here at UVic. She's over at UBC. She's doing programs with school children up at the DAO. We're having a teachers workshop on Wednesday afternoon evening, and then on Saturday night we wanted to have kind of a community gathering for her. So we're going to be meeting. Again, kind of 7 to 10 is usually we were 7:30, but because it's darker, we're going to be 7 to 10 on the Saturday night. And I would love to have people say that they might be able to bring up telescopes if it's going to be a nice night. That would be great. We also need to have people just helping at the front of the dome, helping in the lobby, that kind of thing. So I'll be putting out a call again for volunteers to come and help us with that. We're going to put it out on the Eventbrite page, but we're going to limit it to a number to a lower number of people that will come. Because what I really want this time is for everybody to be able to hear Mary Beth Leisure. Before, on some of the nights when we had 250 and more people there, not everybody got in to hear her because it was so busy and so crowded. So people say, I didn't get to see the speaker. Well, this time I want to have 2, and she even said that she would do it 3 times if there were going to be enough. But we want to be able to have everybody. So we're just going to pull down the number of people that will be there, but we really hope that we'll be able to come out and help us with one more Hawaiian night. I also have got the calendars here. So if you, and many people have already given me their money, look at the green line down here. So there's the calendar. If you have your money with you and you'd like to pick up your calendars, please just see me at the end. There will be a few extra, but not enough for me to kind of start handing them out all over the place. We can put in another order. So if you would like one and we can get you one with this grouping, we can certainly send another order. I think. National, okay. Nothing really new with the national. Everybody's taking along there, so. I'll let you know if anything comes in there. Okay.
I figured out why there was the big bump.
What?
Royals. Royal.
But why would they visit our page?
Maybe it's Royal Victoria, I don't know. But no Russian hacks, don't worry.
Okay, that's all we got for the business portion Does anybody have any questions or comments about the actual business portion of tonight? No, then great, short and sweet. We'll get on to our featured guest speaker for tonight.
Wait,
Oh, Elsie, what you have?
just a brief report on the election that will occur at the AGM in November. We have, it's the tradition of the club and it's described in the bylaws, that a slate of candidates for officers and servers of the club will be presented at the October meeting, which this is. And then an election will take place at the November meeting, which is next month. The slate of nominees for these positions is prepared by what is rather loosely known as a committee. And that is going to be posted on our website tonight or tomorrow, so you'll have a month to look at it. I'd like to just point out who the first 5 of these nominees are. Our board of directors consists of about 25 people, which is rather in keeping with the size of boards of directors of most of the centers in Canada. The nominee for president will be Chris Kurtz. Stand, please. First vice president nominee is Red Country. Second vice president is Glenn Crawford. The secretary nominee is Les Welch. I'm typing way down there. And the nominee for treasurer is Bruce Lane. There are numerous other positions, and you can read all about those when this thing is posted tomorrow.
Okay. Bruno.
Can I say something about law?
Yeah.
Those of you who are familiar with all of it's an annual award for service to the society. And the membership are invited to nominate an active member for consideration by council. So I'm going to suggest that we'll leave it open till the 31st of the month, I believe, which is a Monday, and council will have 10 days or so to finalize, look at all the nominations and draw the conclusions. But the nomination process is open to all members to nominate their members. Okay, we have to do this 45 days before the AGM, so we've done it.
Do anything posted about that on our website?
Eh?
Would you like anything posted?
If you go on the website, under about, I believe it is, you'll see special items there in the board. All the criteria are.
Yeah, the criteria is all there, and the council will follow the criteria with nominees. But if you're nominating somebody, do check the website and make sure that's what it is. Right?
Good.
Okay.
Okay, anyone else? Right, well, I think we all remember our guest speaker for tonight. He's been very kind in speaking to us several times over the years. But for those who don't know him, I'm Dr. Marois, completed his PhD at the University of Montreal in 2004. The main topic of his thesis work was to understand the limits in exoplanet imaging and to design innovative observing strategies. After his thesis, he did postdoctoral researches at the Lawrence Livermore National Laboratory in California, Berkeley, and at the NRC. In 2008, while at the NRC, he led the team that took the first direct image of another planetary system using the Keck and Gemini telescopes. He is currently pursuing his research at the NRC Hertzberg up in the hill here, where he is part of the Gemini Planet Imager campaign and developing instruments for imaging Earth-like planets at Gemini South and the 30-meter telescope. So please welcome back Dr. Christian Marois.
Thank you everyone for being here. Facing the big storm, hopefully you won't get rained out afterwards. So I wanted to change a little bit of subject. I believe the last time I was here I discussed about the Gemini planet imagery. So now this time I want to talk more about the search for habitable planets. So who was at my CV talk? in mid-August. Okay, one person, great. So sorry that double the slides. But for all of you, other people that are going to be a new thought, great. So we know for the last couple of years from the Kepler spacecraft that found numerous possible Earth-like planets. But we need to remember these are Earth-sized planets. They're not necessarily Earth-like. It's a big difference because Kepler only basically know the size of the planets and a little bit about the orbits, but we don't know anything about the atmosphere of these worlds. All that is a bunch of theorists getting together and trying to invent ways that planet form and say, oh yes, it supposedly has an atmosphere, but in reality nobody knows. So the next big thing in our field is to find habitable planets. So we first need to find these rocky planets, so Kepler give us two candidates. The next part is try to characterize them. The problem with these Kepler planets is they're usually very far away. To be able to characterize them, they need to be closer in, so we can actually have a lot of photons, a lot of light from these worlds, so we can then do kind of spectrograph or other techniques to learn about the atmosphere of these worlds and start to see atmospheres with hydrogen, water, carbon dioxide, methane, ozone, and be able to start to say something about how Earth-like these planets are really are. And if you want to look for rocky habitable planets that are easy to characterize, the obvious star to look at are the stars close to us. So let's forget the sun, because we already know. The next one in line is the Alpha Centauri system, which lies roughly a couple of light years from us, only 4.6 light years. You guys will be better than me at number. But what's interesting is it's that system contains actually 3 stars. 2 that are sun-like, roughly the mass of the sun, and one that has a red dwarf called Proxima Centauri. So the likelihood of finding 2 sun-like stars so close to us is very small. So we're very fortunate to have this system so close by to us. So if you want to find something like Earth, having 2 sun-like stars is a pretty good start. Because nobody knows how planets form around stars that are not like the sun, or very little. Kepler gave us some statistics, but getting down to characterization of these worlds, we're not to that level. So today I'm going to talk about the Alpha Centauri system and how people are developing new technique, including us at the University of Victoria, about finding planets that might be like Earth and how we're going to go in characterizing them to see if we can live there in the long future. So if you look at the Milky Way, the sun is roughly 8 kiloparsecs away from the galactic center. So the size of that light laser pointer is pretty much the stellar neighborhood, the region where we're going to try to find these habitable planets where we can characterize them. If you look at this is the sun, this is our Earth cloud, a bunch of debris orbiting the sun at roughly 10 to 10,000 astronomical units and more and beyond. And the Alpha Centauri system is roughly a bit beyond the 4 light years from us. There's the Proxima Centauri. We believe it's actually a bound system. Some people are arguing that Proxima might be simply a nearby red dwarf that happened to be close to Alpha Centauri. It's 15,000 AU from the binary sun-like stars. It's actually quite far away from the Alpha Centauri main system. There's a bunch of red dwarf, very tiny stars that are a bit bigger than Jupiter in terms of size, but they're of course more massive. So of course, having these 2 stars, we're very fortunate. This was very low statistics for us to find something like this. So if you look in terms of distance, so this is the sun, this is the planet of our stars, all of our solar system, all the way to the edge of our solar system. So this is a logarithmic scale. So every time you go from 1/6 is 10 times longer, 10 times more distance. So if you go to the edge of our solar system, which is roughly 100 AU or more, roughly 100 AU, you have to go several, 10 times that, and 10 times that, and 10 times that, all the way to be able to get to Alpha Centauri. So this is roughly 500,000 astronomical units from us. It's very far away. There's a lot of empty space between us and the Alpha Centauri system. So how long would it take to get there? So if you take the New Horizons spacecraft, which is one of the fastest probes that we ever sent from the Earth, it's traveling at 60,000 kilometers an hour, which is roughly 16 kilometers a second. So if you live on the West Shore like me, you want to go downtown Victoria, you get there in a second. So you can say goodbye to the Calgary Club. You get to work in a second. It's a pretty fast spacecraft. And it took 9.5 years to reach Pluto, which again is very close by compared to the nearest solar system. So if you want to travel to that speed, you know, take a ride on New Horizons all the way to Alpha Centauri, assuming you would be aiming in the right direction, it would take you around 8,000 years to get there. It's a long time. Even if you're doing some cardio sleep and you wake up and the world has changed. And it's what's actually interesting is if it takes 80,000 light years, so this is time, and this is the distance of several nearby stars. If you look some stars, if you take the Barnard star, it's roughly 10 light years from us, and it goes pretty close, and then poof, it goes by. Alpha Centauri system, it's traveling at similar speed than the Sun along the Milky Way. It's actually a very broad curve. And if it takes 80,000 years to get there, well, Alpha Centauri is moving away. What's interesting is at some point, let's say in 10,000 years from us, you send a ship, let's say there's a habitable planet around Barnard stars, and you send a ship there, you put the civilization, in a few thousand years, your civilization is going away. So you have to make sure that they can survive because they're moving away quite fast from the solar system. So nearby stars, they come and go. But what's interesting is Alpha Centauri is here to stay for a decent amount of time. So where is Alpha Centauri in the sky? So you need to go to the southern hemisphere. This is the galactic center. Alpha Centauri lies roughly in the galactic plane. If you start zooming in, Alpha Centauri is near the Southern Cross. It's Alpha Centauri, like I said, it's a binary system. This is a two sun-like stars, and the Proxima Centauri is well away from these two. You're zooming again, so you put the star Alpha Centauri A in the middle. This is Alpha Centauri B. Speaking French now, very tired. Alpha Centauri B. It has a slightly eccentric orbit, and its closest approach is roughly the orbit of Saturn in our own solar system. So just imagine a second sun orbiting near the orbit of Saturn in your own solar system. It's pretty weird. And Proxima Centauri is, of course, probably outside in the ring. So this is again a view from the side. So Alpha Centauri, we're in 2016 now. It's slowly getting toward its closest approach to A, and probably 2030-ish, 2035. I think it's fitting there. So it's red. We believe the system is roughly 5 billion years, roughly the same age as the Sun. But what's interesting is the system has a very high volatility in the atmosphere of these stars. So this is telling us that the system probably formed closer to the galactic center, probably halfway between us and the galactic center. And then with some interaction, close encounter with several stars, it migrated outward until it was found close to our own solar system. So it probably did not form at the same separation as the Sun compared to the galactic center. So what is it like? So let's assume that there's a planet there. So of course, you can assume planets in binary system. Maybe think about Tatooine and Star Wars. So what would the night sky look like? So let's say if you put a sun-like star at roughly the orbit of Saturn, your night sky would look like a total solar eclipse, basically. So the light coming from the secondary sun-like star at 10 AU is roughly the light you get the visual light from a total solar eclipse. That's pretty nice. You always have small shadow. Although I never saw a total solar eclipse. You still have some amount of light getting to you. So the habitable zone. So Alpha Centauri, E and B, so solar system, Earth is actually closer to the inner edge of the habitable zone around the Sun. It's around roughly from the orbit of Venus to the orbit of Mars. Of course, Mars and Venus, even if they're inside the habitable zone, they're far from being habitable. Although we can maybe terraform Mars, but that's another topic. So the orbit of Alpha Centauri A, so it's around 0.8 to 2.4 AU, so roughly the size of the habitable zone of our own solar system. And B being a slightly smaller, cooler star, the habitable zone is actually a bit closer in. So the size of the habitable zone compared to different stars, you all know the star Sirius. Sirius is being a very warm blue star. Like stars, habitable zone is actually quite large compared to Alpha Centauri A and B. And look at Proxima Centauri. There's a blue dot there. This is Proxima. So again, this is a very tiny, very cold star. So the habitable zone is very, very tiny. So one big question. So you have two sun-like stars, and you want to look for planets around these. The first question you ask yourself, is it possible? So is it possible to find planets that would be like Earth? Orbiting one of the two stars, if you know that these two stars have an eccentric orbit, and they come very close to each other. And some people have looked at that. It's actually a pretty recent paper if you look at 2016. And people have looked for stable orbits. So the first question you ask yourself, are they a stable orbit? And if you have a gravity simulation model, and you have star A and star B, and you put the habitable planet around one star and you spin inside the habitable zone, is the second star at some point going to interact with this orbit and eject the planet from the system? So that's a big question, because if it's not stable, there's no point of looking for habitable planet around any of these two stars, because physics, and we believe we understand how these interactions happen. So people will look at that, and so all these this is inclination, so this is mutual inclination. So this is star A and star B, they orbit in the plane. So the question is, can this planet orbit that way or orbit that way? How is it affecting its stability around that star, depending on what orientation it's orbiting the star? So an inclination of 0, a mutual inclination of 0 would be the planet orbiting the star A in the same plane that A and B are orbiting each other. So if everything is the same plane, you can get, so everything is red here, means it's a stable orbit. So remember this, the habitable zone is around roughly 1.6 to 2.4 AU around star A. And for mutual inclination of 0 all the way to 45 degrees, there's a wide range of stable orbits around that star. And the same for, so this is star A, this is for star B. Again, there's a lot of stable orbits. So yes, you can put a habitable planet, a small rocky planet like Earth, around any of these two stars, and it's stable. Okay. It survives for, well, here they only run it for, I believe it's 100 million years to be a year. But it's compromising that you have stable orbits around these two stars. And this is a projection of these stable orbits in the sky. So you see there kind of ellipsoid because of the inclination of the system related to us, but that's a good news. So the second question you could ask yourself now, can we form planet inside a binary system? This is actually a much harder question to answer, because we don't yet fully understand how planets are forming around stars. So some people have been looking into that, because people have been dreaming about planets around Alpha Centauri for decades, if not centuries. So people have run planet formation model with putting small pebbles around stars, and when they come close to each other, they glue themselves, and then they continue until they get something else, and they glue together, and see if they can actually form planet core with the secondary star flying by every, I don't remember the period. Is that 80 years? Yes. I don't remember these two stars. Anyway, so the second star is zooming across at 10 AU every 80 years or so. And see if there's enough stability enough an environment suitable to form planets. And the answer is well, yes. If you look at Alpha Centauri A and B, here less than 2.5 AU around A, which is the stability limit. It did manage to form after 200 million years 1, 2, 3, 4, 5 object around that star. And the same thing for Alpha Centauri B. It did manage to form planets. So then you can ask yourself, did Kepler form planets around binary? And the answer is yes. So there's nothing preventing you from forming planets, and it seems that they are stable orbits around these stars. So it looks quite promising. If nature did produce rocky planet around any of these two stars, then it could be happening. There's nothing in what we understand about the physics of planet formation and the stability of a system with two stars that prevent having rocky planets orbiting these two stars. So the big question then is, are there little planets around these stars? And what about Proxima? Because of course Proxima, I'm not talking about stable orbits and planet formation around Proxima. It's so far away from these two stars that we believe if there's any planet forming or did form around that star, it probably happened like it was an isolated star. The planet formation for M-dwarf is again subject of another talk. But there was a big result announced last August with a field red dot campaign, which was run mainly at VLP in Chile, at ESO. Well, they did find 2 or 3 years ago a candidate, but it was a very, very low SNR, so it wasn't significant enough to go ahead with a publication. So we found a planet around Proxima. Because if you're claiming this, you better have very good data to convince people. So they managed to convince the VLP tag. And I was told by other people that were not part of this team that people have been trying to do this for like more than a decade. Always turned down. Because look at the number of lines that you need to be able to fully convince yourself that this is there's an habitable planet around Proxima. And it was actually just politics that prevented this discovery to happen 10 years ago. As people were using this is in a way this is a fishing expedition. And telescope allocated committee hate fishing expeditions because they're spending a lot of taxpayer telescope time with no guarantee that it will succeed. And this is hard to convince people to go ahead with a campaign that requires many nights of observation to be able to make a discovery. Until somebody had said, oh, we have a glimpse, there might be something there. And that was enough to convince the tag. With a new way of processing the data, that they pick up this little 3 sigma bump. And that's how they managed to convince ESO to give them the time to do a very clean run. And that's where the discovery was made. So it's not because people just got brighter. Well, part of it they got brighter at reducing their data and extracting the signal. But the first step of preventing discovery from happening a long time ago was politics and telescope times meetings. So I hate the telescope meetings. That's a subject on another one. So they unveiled, so it actually the news went out 2 weeks early. So a German paper said, oh, they're gonna announce a planet around Proxima. They announced it 2 weeks later. That's a UK land team. So the main star is the Proxima B. So this is the closest star to the sun, which is quite exciting because having a rocky planet so close to the sun is amazing because then you can dream about very detailed characterization of that world. As I'm going to say in a few slides, it will not be easy. So don't hold your breath. So the big question, so a few years ago, people have announced the discovery of an Alpha Centauri B. I don't know if you're following the field, and it was then shown it was not real. This will not happen for this planet. It's a very, very, very strong detection. So this is the false alarm rate, basically, and it's way below 0.1%. So on Earth, there's some very, very, very weird flaring happening at dawn and days over more than, I think it's 15 years worth of data. This thing will survive scrutiny by other teams. So this is a real thing. It will not disappear in a year or two saying, oh, it was just statistics error. It's very, very unlikely this is happen. So this is a real discovery. So this is the sine wave. So these are radial velocity detections. So they have not seen the planet itself. What they're seeing is the effect of the gravity of the planet that's pulling on the star itself. So planets orbit the star, but the star also orbits the planet. It's just that the star is so much massive than the planet that the star is only moving slightly while the planet moves around. So this little motion in the sky, you can pick up with the spectrograph. So the spectrograph will split the starlight at very high resolution. And usually this spectrum has a bunch of very narrow lines, like a cone, basically. So when the star is moving toward you, the line is moving toward the blue. And when the star moves away from you, it moves toward the red. So if you have a little software that's tracking the position of these lines on your detector very precisely, you can see that motion happening. And you're getting down to a meter per second, which is, that's speed, basically. So, this is pretty slow, but these spectrographs are so sensitive and so stable they can actually pick up that speed from light years away. So these are amazing instruments. I can tell you, they fit in a bunker with milli-Kelvin temperature control, with pressure control, because nothing needs to move. Make sure that you're sensitive to that accuracy. So this is a bit of a number, but I'm going to just point to the important numbers. So the period of the planet is only 11 days. So again, much shorter than the Earth. Semi-major axis, the size of its orbit is 0.05 astronomical unit. This is extremely close to the star. The star. So this is the light emitting by the sun, which is roughly peak emitting where our eyes has the most sensitivity in the yellow. Well, this star emits most of its light at 1 micron, which is an infrared wavelength. So if you go there, you're going to see a very dim red star with most of its energy coming from the infrared. It's a very, very, very different beast than the sun. So to give you an example of the size, this is the sun, its diameter, and Mercury's orbit. Well, this is Proxima, the star. This is the habitable zone, and this is where Proxima orbits. So it's actually quite close. It's very, very tiny space around the star. So the challenges for habitability. So the big question that we're finding this planet is, are there alien on it? Everybody's asking that. And is it habitable? Is there life? Is there continent, water? Well, and dwarfs, like these little, very red dwarfs, are very peculiar. First of all, the planets have been so close to the star that it's probably what we call tightly locked. So it's always facing the same face toward the star. So you don't get this day and night cycle. One side always see the star, and the other side never see the star. So that can be quite bad because one side can actually freeze, while the other side can actually burn to the ground. Unless you have very good atmosphere where you can circulate the heat to make sure that you have a temperate climate, even on the dark side. But then you have strong winds and stuff like that. It's not impossible, but it doesn't start in the right direction. The second problem is these stars are flaming like crazy. So they send big flare. The star gets brighter, gets dimmer. It sends a huge amount of UV and X-ray toward the planet. So X-ray and UV means sterilization. So you need a planet that would have a big atmosphere, has some kind of magnetic field to protect itself from the deadly particles, and UV also have ozone and stuff like that. Big atmosphere to be able to resist to that amount of radiation coming from the star. Also very strong winds, coronal mass ejection, close to 2,000 times what we get from Earth. So again, people are wondering if these constant flaring and ejection would actually strip the planet from its atmosphere as a function of time. So if you keep doing this over 5 gigi years, at some point you ran out of atmosphere. It has a very red spectrum of vegetation, if there exists. It's probably very different than ours because they can't really do. They can't really absorb a lot of green light to do photosynthesis because there's very little green light. So if there's life on it and vegetation, it probably evolved in a way that's very different than ours. We're not sure if that planet actually formed at that location. It might have formed further away and then migrate inwards. Or if it actually formed there. If it's formed there, there's some other challenges that we'll talk about. If you want to have water on that planet, it's actually not trivial how to get water so close to the star. That's separation. It's a bit colder than the Earth. The Earth average temperature, the black body average temperature is around 255 Kelvin. This one is 240. So it's a bit colder than the Earth. And of course, you have this big AB sunlight star that might play and have some gravitational influence on the planets. So if you look at the habitable zone around that star as a function of time. So this is the number of time. So this is after a million years of formation, the habitable zone was actually much further away because the star was brighter and it was younger. And after a while, after a billion years, the star is getting dimmer and dimmer. So the star, the planet is currently inside the habitable zone, but it's actually formed there. At the beginning of the system, it was well off the habitable zone. So if it formed there, it was probably too warm. The water, the ice line was probably over there, so that's where the water is, and it would be a very dry world. So if we need to form further out to get the water, and then migrate by the various processes all the way to be able to get there at the end of 5 million years. So I read almost 250 pages over the last 2 days. This is quite amazing. This published this at the end of August, and inside a week there were 250 pages worth of analysis of that planet on the web. That was submitted or published by teams. So some team, it's obvious that some teams got the tip about the discovery well before the discovery was made public. But after reading this 250 pages, the end result is it can be anything. So that was quite frustrating. So that's why don't believe your ears. Just believe your observation. So basically, it could be a mini Neptune. So it's roughly 1.22 Earth mass, but this is the minimum mass. If the planet has an inclination, it's actually more massive than that. It could be all the way up to 3 to 4 times the mass of Earth, if it's very inclined. So if it's very inclined, it could be a mini Neptune. So a small rocky core with a huge, gigantic atmosphere that's no way habitable. It could be a Venus, it could be a Mars, it could be a Europa planet, a big ocean, a big ice-covered world with water, liquid water underneath. It could be a Mercury, basically, with big rock with no atmosphere. Well, it can be Earth-like. So after 250 pages, it can be anything. There was a nice paper about the various consequences of having a synchronous rotation, so having a tidally locked system, or somebody or a planet that has a 3 to 2 non-synchronous orbit. So it's actually slightly rotating as a function of time, a bit like Mercury. And depending on how much water and CO2, so if you have CO2, you can you can trap a lot of heat inside. You can warm up the planet, have liquid water. So they have this regime where you have liquid water on one side, it's frozen on the other side, or it's liquid everywhere, or it's partly liquid. So, like I said, it could be anything. So they have nice 3D maps. So these are 3D maps. Depending on how much CO2, this is temperature. So the region where you're facing the star gets really warm, so 255 Kelvin. On the other side of the planet, where it's always dark, you go down to 145 Kelvin. So this is minus 130 Celsius. So it's colder in Canada. and then as the warmest point is 255 Kelvin, which is what, 90 degrees Celsius. This is worse than Arizona. So depending how much CO2, so if you lower the CO2 and you add some N2, get the name, nitrogen, thank you. If you put nitrogen here and you have a synchronous orbit, it gets really cold and sort of warm. So if you want to find a temperate region where life could develop a bit like Earth, you need to be close to the terminator. This is where it's around 20 degrees Celsius. So if you go to the middle, it's way too warm, and if you go to the night side, it could be way too cold. And there's also estimates of ice, depending if you have an ice-covered planet, you can have an ice thickness all the way up to almost, I guess, 3 kilometer thick ice, which is crazy. So our own telescope, the MOST telescope that was developed a long time ago by Gordon Walker and a when Jimmy Matthew was leading the project at UBC. It's a small suitcase spacecraft, roughly that big. It's only taking broadband photometry, and it's been going for, I don't know how long, it's over 10 to 15 years. It's been running for quite a while. And I remember Gordon Walker asking me to take a bet that he wants to buy 6 months. I should have taken that. Especially after every month you give me twice the amount of money. So they were doing actually a campaign while this discovery was announced. The most telescopes were just finishing a campaign to look for flaring and maybe a transit around that star. So people were already trying to do this in real time. So they rushed their paper after the discovery was announced. And basically, they did not find any transit. But they did find some very big flares, so these are flare events. The star went up by almost 25% brightness, which are 30% brightness, which is pretty big variation of intensities. You try to follow their signal to try to see signal in transit. You do see something, but it's not strong enough to claim a discovery. They're not sure if these are flare artifacts or actually transit of the planet. So you require more work and more precise data to really rule out the transit of the planet. If it doesn't transit, characterization of that planet will be an order of magnitude harder. If it transit, then you could put James Webb on it. It's going to be great, amazing work on proximity. If it doesn't transit, then yeah, it's going to get more complicated. So what's next? So what if it doesn't transit? So if it transits, it's James Webb, it's a no-brainer. We'll know the answer in a year, 2 years, 3 years. 3 years from now. If it doesn't transit, then you have to be more clever. So people like suggest that you James Webb again, but do it at 10 micron. The nice thing about the 10 micron imaging is you're sensitive to the thermal emission of the planet itself. So if it doesn't have an atmosphere, or if it has an atmosphere that doesn't circulate the heat, one side is going to be really warm and hot, and the other side is going to be cold. So as the planet moves around, what you're seeing from the planet, its phase is going to be changing, like the phase of Venus. So when the planet's going to be between you and the star, you're going to see the cold phase, the cold side of the planet. So the 10 micron fell is going to go down, and when it moves around, it's going to go up again. So that signal, that phase signal is going to tell you about the atmosphere. And you can do this at several bands around in the 10 micron regime, and you can find ozone and other methane and water, etc. You can actually start seeing atmospheric molecules in the atmosphere on that world. But it requires more than 1,000 hours of James Webb time. Good. They also have a pack. So it's going to be hard to get that amount of time to be able to do this. But it's maybe possible. And the pressure factor to use James Webb is going to be probably 20 to 1. So they're going to be 20 times more proposal than they have time on the telescope. It's not 50 to 1. So asking for 1,000 hours on a single object, it's going to be asking a lot for the telescope community, allocation community. There's an interesting approach suggested by using the VLT instrument with the sphere instrument, which is an adaptive optics system to correct the turbulence in the air to give you very sharp images. This is our competing instrument compared to GPI, our own instruments. We are very similar. These expressors are very high resolution spectrographs, so they looking into combining these two instruments together to put a bundle of little fiber optics in the beam of sphere and decouple the light in the visible and try to see the planet signature. So it basically would look like this. So even if you're not seeing the planet in the image itself, given that the star doesn't have, let's say, oxygen, but if the planet has oxygen, the oxygen is a very, very narrow line in the visible. So you could actually, if there's a Doppler shift, you can pick up the oxygen line of the planet inside that mess of light coming from the star, and a very tiny speck of light from the planet, and be able to produce an oxygen image and pick up the planet. That would require 300 hours of telescope time. So not easy. But people, maybe people are going to try the 2020 regime, so maybe 4 years from now. And of course, the end result will be to do this on an ELT, like the 30-meter telescope, if you're going to the south, or the ELT, the European equivalent, that's in Chile. And so this is more 20, 30-ish observation, but you can do it in 10 hours with a 30, 40-meter telescope. So the sheer increase of diameter increases the capacity to do science by factor 30 in terms of visibility. Which is pretty good because 10 hours you can actually feel the motion of the planet. While 300 hours the planet moves around, so it's hard to track and be able to combine the data to get the signal. Well, 10 hours is a lot better. So we were kind of beaten in Canada with this Proxima Centauri discovery. René Doyon and in Montreal and Jean-François Donati in France are building a spectrograph and their equivalent called NERPS in the southern hemisphere. So this is an infrared high-resolution spectrograph to look for planet and all these red dwarfs. And it's scheduled to be on sky next year. So too bad we missed that discovery by a year. But it's very proud. We're very proud of the instrument was partially built here in NRC, and it's looking quite good. And this instrument should find quite a lot of these nearby proximity planets. It's going to be surveying all the nearest M dwarf in the solar neighborhood to find these rocky planets. So give us maybe up to 2019, and we should do a lot more about planet like Proxima Centauri B, but around other stars, like Varna stars, or Wolf 359, stuff like that. Kind of stars. So going back to Alpha Centauri A and B, finding habitable planet and rocky planet around these stars is not going to be easy. Proxima B is nothing compared to that. Guarantee you. People have played discoveries in the past, but they all were shown to not be real, like the Dimory paper in 2015 called they thought they found a planet around Alpha Centauri B. The current mass limit inside the habitable zone by the radial velocity technique is roughly Neptune mass. So currently, no one knows if there's a habitable planet or rocky planet around these two stars. It's Terra Incognita. Nobody has the instrument capable to do this. But what imaging? What we could do with imaging? So if you consider the Mount Everest like the sun, and you're looking for a rocky planet around a sun-like star. So this is the sun-like star. And you're looking for a young gas giant like Jupiter. You're looking for a football field-sized object. If you're looking for an old Jupiter, this is a baseball-sized object lost on Mount Everest. And if you're looking for a rocky, habitable planet, you're looking for this little red spider walking on it. This is quite hard. So approximately, you do this in duplication. So, but one solution that I've been thinking for a while is to use 10 microns. So the same reason why you would use the James Webb Space Telescope to directly image Proxima B at 10 micron, you could do this on the ground to look for a planet around Alpha Centauri A and B. So this is the Earth and the Moon, and this is the Earth and the Moon at 10 micron. So you see what's interesting. In the visible, you see a phase, but at 10 micron, there's no phase because the atmosphere circulates the heat very efficiently around the Earth. So even if you're on the white side, or the bright side, the sunlight side, or the dark side, the Earth doesn't have time to cool off. The night side that much. You don't see it change. While the Moon here, you do see a decent phase from the bright side to the dark side. And what you see again is the clouds. Clouds are annoying. Clouds are high up in the atmosphere, and they actually block some amount of heat. So the planet gets a bit dimmer because of the clouds. But what's interesting is the contrast. At 10 micron, you're actually instead of looking for this little red spider around Mount Everest, you're looking for that big football-sized object. But the contrast at 10 micron is much better. And what's even more interesting at 10 micron is there's actually biomarkers, the stuff you're looking for to see if the planet is habitable. If you have CO2, you have ozone, you have methane and water bands inside that regime. So you can already, if you make a discovery and you do a spectrum of the planet of that band, it's telling you right away a lot of biomarkers. So you don't have oxygen, that's the only thing missing. But you do have a very good idea about the kind of molecule inside the atmosphere. And also, if you look, this is the black body emission, it gives you an idea of the temperature of the surface of the planet. So you can already know is it 200 degrees or 400 degrees Kelvin. So can we do this now? Well, we have 10-meter telescopes. So if you have your optimized instrument right now, you go to Chile at VLT or Gemini South, and you point your telescope toward that star, can you resolve this little rocky planet compared to the star? So this is the habitable zone of A and the habitable zone of B. This is the star in the middle, and this is your diffraction limit. So this is the maximum of what you can do right now with your telescope. As you see, the telescope has a resolution. It's actually big enough to be able to see habitable planet around Alpha Centauri B. So we can do this now. There's nothing preventing us from doing this. So we started a project at Quebec to do this, to build an instrument that's basically aimed at two stars, Alpha Centauri A and B. Operating at 10 micron, that could directly image a planet like Earth around any of these two stars, giving enough telescope time. So the goal is to go to Chile at Gemini South, which is an optimized telescope for the infrared. So this is a simulated image of Alpha Centauri A after 100 hours, assuming if we get it going pretty soon in 2019. So can somebody find the planet? Once. Or there's somebody pointing. So this is B, Alpha Centauri B. The stuff in the middle is Alpha Centauri A, residual light. And this is Earth. So if you have 100 hours, which is roughly 10 telescope nights, which is not that much, 10 to 20 telescope nights, of observing every night Alpha Centauri A, nonstop, you do get the sensitivity to be able to directly image another Earth. And be able, well, characterization is going to be hard, so you probably will have to wait to with the ELTs, but you can imagine going to color the Gemini, and that will give you an idea of the temperature of the surface of that world. It has a black body emission and stuff like that. And of course, that would trigger as well a bunch of other calculations, because people would like to know if there's an atmosphere visible, get a reflected light instead of thermal emission, and that would open up a huge amount of work that can be done in that star. So one other question is, what would happen if you bring this unique instrument to TMT? So let's say TMT goes in the south, has 3 times the diameter, you get almost 10 times more flux in 2028. So this is the same star, the same Gemini object, the image with Alpha Centauri A and B, with the Earth right there, 100 hour and an 8 meter. If you go with TMT with only 25 hours, you get this. So this is the Earth, which is the brightest object in the solar system at 10 micron. We get Venus, we get we get Mars, and we get Jupiter. So only 25 hours of TMT, and you get the full picture of another solar system in the thermal emission. So this is what a 30-meter telescope gets. It's maybe costing $1.4 billion, but you do get quite a bit of interesting science out of it. And of course, you can imagine this is for Alpha Centauri A and B, but you can look at other stars as well. You can go further away in space, and start looking at other sun-like stars all the way up to roughly 10 parsecs. After that, you need a 100-meter telescope, which will cost $10 million. Little. So if you do find it, so there's, like I said, a 10 micron. So just making that discovery is the first step. Then you want to make multiple observations, because you want to trace its orbit around the star. You can get the color temperature will give you an idea of the surface temperature, because it's ozone at 9.5 micron, you see water, CO2, methane, and you have an idea of the radius of the planet as well. If you have the black body emission, you can derive a rough radius of the planet. So what about even further in the future? So people, especially in the US, are working on 2 large-scale telescopes beyond James Webb. So James Webb has almost 6.5 meter and $6.5 billion. It's a $1 billion meter. So they're looking at the Louvre telescope. It's just between a 10 to a 15 meter telescope. So it's a copy of James Webb, but more like HST working than visible. So much bigger than, so this is James Webb, and that would be the Louvre kind of instrument. And the ABEX, which is a dedicated 6.5 meter kind of James Webb-like telescope, but dedicated to exoplanet imaging, using what they call the Starship, which is basically a very expensive thumb that blocks the starlight to be able to see the planet, just without. And these are the kind of images that are visible you could get with such instruments. So this is, again, Venus, this is Earth and Jupiter, and seeing the planet and reflected that gives you very complementary science of what you can do at 10 microns. You can get oxygen, and you have a lot of information about the atmosphere as well going into invisible compared to 10 microns. So they're very complementary approaches. And of course, our project costs $1 million, and theirs will cost $10 million. Different scales. But in the visible, you can look at other kind of stuff, very interesting. science, you can look for the red edge. So if the planet is habitable and like Earth, you can see the vegetation, the red edge at around 0.7 micron. If it has a lot of green region of the planet, it's vegetation. If you can even map the surface. So even if you're not dissolving the planet itself, if you have the right orientation of the planet and you track it as a function of time, you can map Earth. You can map the continent of that planet. It's been done for Earth from a distance using epoxy mission. So if you track the Earth with only 1 pixel of light, you see it blinking as a function of time. And depending on what continent you're facing, you're reflecting different amount of sunlight, and you can decouple and get the surface of the planet even if you're not dissolving it. So this is what's Earth, and this is what they derive from their experiment. So this is pretty cool. You can be light years away and map the surface of another world. You could see, if you run this with a different epoch, you can see the various cloud coverage. You can see snow and ice appearing and disappearing from the planet. So have seasonal changes, etc. as the planet moves around. You can do a very interesting and great science. So if you go even further in the future, in the last couple of minutes, what about going there? People have been dreaming about Star Trek and Star Wars. Well, can you imagine ways to get there? But using real engineering and what can be done in the real world? Well, some people are thinking about this, and they actually announced earlier this year, in April 12th, the Starship project, which is basically sending a credit card digital camera at 20% of the speed of light. So the idea is you have a big 4-ish meter cell that's very, very reflecting with a very tiny credit card camera. And then you use a ground-based laser array that you shine the cell for a few minutes. And you accelerate this at 20% of the speed of light. And you can reach up a century in 20 years. So that would be a progress. You don't stop. When you're there, you need to know where the planet's very exactly. And you aim it to pass around 1 AU from the planet at 20% of the speed of light. And you have 2 hours to take images of the surface of the planet as you zoom in by. And after that, you try not to hit the planet, because then you can start the war. Well, they did do the math, and it was actually exploding the atmosphere. It would be a big flash of light. And of course, it's to pave the way to even further away in 200 years to send colonists to these worlds. Of course, this is a very long journey, taking probably centuries, so you need to plan out all water, oxygen, recycling, and community living for a long time to reach these worlds. But you can ask yourself, when is a good time to go? Well, first you need to get $1 trillion to build these spacecraft and understand life in space for centuries. So if you take the New Horizons spacecraft, that took 78,000 years, or roughly 80,000 years to reach Alpha Centauri. But you ask yourself, well, if you design 500 years later something that can go there in 5 years, well, is there a problem? So that one's gonna say, oh, when you get there, like 1,000 of years earlier. So until you can derive a very easy math equation. So if the travel time to get there needs to be less than 2 times the time, twice the time that it takes to develop a system that gets you there 2 times faster. Because if you don't have that, then your second spacecraft will arrive before you. That's that. It's actually a very nice, I believe it's Arthur C. Clarke book about a colony that was sent to another world. By the time you get there, it was already colonized because they sent faster spacecraft. Well, that's kind of the problem we have here. So until you find a way to get there fast enough that somebody will not beat you there's no point to do. So yeah, we need to develop technology and start do that faster. So conclusion, so of the century, the system is not a focus, I think, worldwide for habitable planets, especially with the discovery of Proxima b. But I think people are also very motivated at finding planets around Alpha Centauri b. I think That's really opening up a lot of amount of possibilities, seeing that one exists right there. So it'd be crazy enough to have these planets also in a century A and B. We know that Proxima B, while very interesting, if everybody wants to learn more about this planet, it's very unlikely to be Earth-like, given that it's an M dwarf, and an M dwarf is probably not the best place to be, given the various challenges that I talked about. A rocky planet could be detected now, like tomorrow night. If we have the right instrumentation, 10-meter telescope, and looking at the bus into A and B. So with this project, we could be trying to get started and talking with philanthropists in the US and here, trying to get this funded and get going as quickly as possible. So if you have this 10,000 friend to buy this book, tell him to talk to us afterward. Characterization of Proxima B, probably James Webb. There might be some ground-based opportunities, but it's going to be quite hard. You might have to wait for the ELTs in 2025 to 2030. Bi-thermal imaging on an 8-meter telescope, but that field can really open up with the 3-meter telescope. All with hydrogen spectrograph as well. Move forward, having future spacecraft, the $10 billion plus spacecraft, that's 2030 and beyond. And yeah, people are gearing up to try to go there because we want surface images and trees and lakes and oceans. So the field is quite exciting. So who knows what it's going to be in 20, 30 years. Thank you.
Any questions? Can you tell me, is there some inherent reason why observation stations in 10 micron band are so slow and time consuming?
So the question is, why it takes so long at 10 micron? So the problem is very simple. It's our atmosphere. If you put this 10-meter telescope in space, it would take minutes. But yeah, going in space with a 10-meter telescope, it's $6 to $10 billion. It's quite expensive. But people are looking into James Webb. James Webb is sadly not big enough for this. 10 meter is really the minimum size to be able to do 10 micron imaging on alpha cent. 6.5 meter at 10 micron will be lacking the resolution. And also you're lacking the instrumentation to do this in space. You don't have a chronograph, an highly efficient chronograph and wavefront control at 10 micron to be able to reach that contrast to see the quantum. For a 10-meter ground-based telescope, like I said, you're fighting the atmosphere, you're fighting the telescope. That's warm. You're looking for a 280 Kelvin object using a 280 Kelvin telescope. So your telescope is a light bulb for us. So you need to kill that light. So in theory, you would need to go in space with a 10-meter telescope and cool it down to 5 Kelvin, and that would be amazing. With the right instrumentation to kill the speckle from the light from the star itself to reach that contrast, you would get there in no time. It's really just atmosphere and telescope. And if you go to 30-meter telescope, then you do the math, and you gain by the d to the 4th power in integration time. So something that's 3 times bigger is 3 to the 4. So it's 3 times 3 times 3 times 3 faster. So instead of 200 hours, we're talking about 5-10 minutes. So TMT is going to see, if it goes in the south, it's going to see an Earth liner on alpha cent in 5 to 10 minutes of integration. It's crazy. Well, it takes 100 hours on Gemini. It's that fast. It's crazy how fast it goes. More questions? Yeah.
You mentioned that the Alpha Centauri system may have formed or thought to form much closer to the center of the Milky. Is there any reason to think that the composition of the gas cloud, the minerals and molecules, organic and others, that condense to form planets would have been different? Composition of the parent gas cloud close to the center versus our neighborhood?
This is a very good question. So the question is, if Alpha Centauri and Proxima form closer in the Milky Way, would the matter that formed planet be different And I actually don't know the answer to that question. It's a very good question, and I don't think people know precisely how planets form around these kind of stars and what kind of diversity you get going all the way to the center of the Milky Way and how that can impact planet formation. We're looking for planets in the solar neighborhood, so understanding all the way down to a few kiloparsecs from the galactic center, which are quite far from that level. But what you expect is that it will have more heavy metal when you go closer in. So you might expect more iron-based planets and rocky core planets. That would be my wild guess. I think people have a lot to do before they can answer that kind of questions.
No other questions? All right. Well, thank you. So we'll call adjourn the meeting. Don't forget to, if you want to come up for coffee and cookies, everyone's invited. If you don't know where it is, just follow us up and just come on up and introduce us if you want to know more about us or just hang out and have coffee. If not, we'll see you at the AGM in November.
Okay.